Synchronous motors, as the name suggests, operate at a constant speed regardless of the load. They are known for their high efficiency and are mainly used in high-precision applications. This constant speed characteristic is achieved through the interaction of a constant magnetic field and a rotating magnetic field. Like other motors, synchronous motors are composed of a stator and a rotor. The stator core is made of laminated silicon wafers and is insulated with a surface coating to minimize current and magnetic losses. The stator uses a three-phase winding, and its phase sequence is the same as the rotor's. The magnetic field coil is powered by a three-phase power supply. The rotor is excited by a DC power supply to form a rotating magnetic field that rotates at synchronous speed. The rotor itself can also be a permanent magnet. The rotor of a synchronous motor generates a constant magnetic field, and the stator generates a rotating magnetic field. When these magnetic fields move in the same direction and are aligned, the opposite magnetic poles of the rotor and the rotating magnetic field will attract each other, causing them to magnetically lock. This means that the rotor will rotate at the same speed or synchronous speed as the rotating magnetic field. The synchronous speed can be easily controlled by adjusting the power supply frequency of the motor, allowing for precise speed control. But if the rotor has no initial rotation, the situation is different. Initially, the rotor is attracted by the south pole of the rotating magnetic field and starts to move in the same direction. Due to the inertia of the rotor, the starting speed is very low. When the north pole of the rotating magnetic field turns over, it will generate repulsion with the north pole of the rotor, thus hindering the movement. The starting synchronous motor cannot start automatically. In order to achieve self-starting, the tip of the rotor magnet is cleverly installed with a squirrel cage arrangement during startup. Initially, the rotor magnetic field coil is not energized, so the rotating magnetic field will induce a current on the squirrel cage bars, causing the rotor to start rotating. Similar to an induction motor, after the rotor reaches its maximum speed, the rotor field coil is energized. The rotor is locked on each magnetic base of the rotating magnetic field and rotates at synchronous speed. When the rotor rotates at synchronous speed, the relative motion between the squirrel cage and the rotating magnetic field is zero. This means the force and current on the squirrel cage rod are zero, thus achieving synchronous operation. As long as the load is within the motor's capability, the synchronous motor can produce a constant rotational speed regardless of the motor load. If the external torque load exceeds the torque produced by the motor will lose synchronization and stop. Too low operating power supply voltage or too low magnetic field voltage will also cause the motor to lose synchronization. Synchronous motors can also be used as alternators. Synchronous motors have a wide range of applications. The rated power is usually between 150 kilowatts and 15 megawatts. The rated speed ranges from 150 RPM to 1800 RPM. I hope you learned something new from this video. If you did, please give it a thumbs up and let me know what you think in the comments below.